Hello everyone, this is Professor Keen. We have been talking about Galileo's dialogues concerning two new sciences. Remember, the first science that he's interested in is understanding why certain materials are hard to break and other ones are fairly easy to break. We're looking at Chapter 6 in a student's guide through the grade physics texts, and this corresponds to Galileo's day 2 of his dialogues. In my previous lecture, we went through Galileo's proof of the law of the lever in some detail. Remember, he started from a simple axiom that was intuitively obvious and used geometry to demonstrate the truth of the law of the lever. So what we're going to be doing now is taking the law of the lever for granted and seeing how it can be applied to understanding why it is that certain materials are harder to break than others. Specifically, we'll be looking at the example of beam breaking. Galileo spends quite some time discussing this, and you'll notice in this chapter there are a lot of fairly in-depth and complex mathematical proofs of some propositions. So try not to get too hung up in the details of the mathematics. What I want to do is lead you through some of the main ideas and explain the ideas behind his propositions in a semi-mathematical way to give you a flavor for what he's doing. His mathematical proofs are actually very interesting and very carefully worded, and it just takes some time to go through in detail. If you'd like to go through them in detail, I encourage you to do so, but it's not going to be absolutely necessary that you do so. Okay, so this lecture we're going to be focusing on the topic of from the law of the lever to beam breaking. And again, this is from A Student's Guide, Volume 2, Chapter 6. You'll remember in one of my previous lectures, I made a distinction between longitudinal force and transverse force. So let me remind you what we mean by longitudinal force. So the longitudinal force required to snap a beam depends on two things. Depends on two things: the material out of which it is made, out of which the beam is made, the material, and the cross-sectional area. So the longitudinal force required to snap a beam depends on the material and the cross-sectional area. So let me draw a picture of what I'm talking about. Suppose we have, here I've drawn a cylindrical beam. This could be a square cross-section, a rectangular cross-section, an I-beam, whatever you want. But if we try to pull on the end, that would be the longitudinal force. And how hard you have to pull it in order to crack this beam depends on what kind of material it is. That's an intensive property. It could be either copper or aluminum or steel or wood or styrofoam. The material obviously has an effect on how hard it is to break it, and also the cross-sectional area. So how much of the beam is there? So you might think about if the beam, if this was like a piece of spaghetti, let's say, and you were trying to break it this way, it would take some amount of force. But if you had two pieces of spaghetti side by side, there would be twice as much cross-sectional area. It would be twice as hard to break using a longitudinal force. So the longitudinal force that is required to break it is proportional to the cross-sectional area of the beam. So this, how many square centimeters or square meters there are, for example, that the area comprises. Okay, so that's the cross-sectional area. Okay, now how should we be thinking about this longitudinal force? We can kind of think about this longitudinal force as a tendency. So this longitudinal force required to break it is really a tendency of the parts of the beam to stick together. The internal parts of the beam to cohere. stick together, right? And, you know, Galileo had speculated on the cause of the coherence. Are there these internal vacua that are holding it together, or is there some internal gluey substance? But whatever the cause of this coherence, there is a tendency of these things to cohere together, and we can think of all these tiny internal forces as adding up to create this a resistance to a longitudinal force that's trying to break it. So you might think of, let me draw it like this. So if we're kind of going a little bit beyond what Galileo discusses in this chapter, but that's okay. Let's suppose you have some beam like this and you're trying to apply a longitudinal force to break it. As you do so, let's consider a cross-section inside of the beam. What happens is all the little internal parts of this are all sticking together. So there's all these kind of little internal forces, these resistance forces that are pulling back like this, trying to balance out this longitudinal force that you're applying to it to try to break it. And we could add up all these little internal forces, and as long as those are big enough to overcome this, then this beam will cohere, it will hold together. And if they can only get to some maximum strength, and then you exceed the sum of all these with your longitudinal force, then the beam is going to break. So if we take all these and kind of add them up, we might imagine that the overall kind of the maximum that they can achieve, we can summarize those with an internal resistance force. So this R right here is an internal resistance that is able to get to some maximum amount in trying to overcome your longitudinal force. And if you exceed that maximum internal resistance force, then it will break, right? So let me write that down. We can consider all these internal forces as a single resistive force. This is kind of a simplification that gets larger and larger and larger, so as to attempt to balance the longitudinal force that you are applying to the beam to try to break it. And it can increase, so R, this resistance force, can increase up to some maximum value. Some max value. And that maximum value, like I said, depends on the kind of material and the cross-sectional area of the beam. Okay? After which it can no longer hold the beam together. The beam or the prism or whatever you're trying to break. Okay? So we're trying to come up with some description, some internal description of what's going on as you're trying to break it. And Galileo calls this, they call R the longitudinal resistance. My tablet froze up, gotta wait a minute. We call R the longitudinal resistance. Of the beam. Okay, I hope that makes sense. R is the longitudinal resistance of the beam. Okay, now the question that arises naturally, and this is one of the things that Galileo is aiming at, is why is it easier to break a beam with a transverse force than a longitudinal force? So why is it easier to break a beam using a transverse force than a longitudinal force? you might remember what we mean by a transverse force. If we have a wall, I'll make a sketch right here, a wall, and suppose there is a beam that is sticking out of the wall by some distance. Maybe it's embedded. You might think of this as a stone wall, and we're looking at it from the side. So this right here is your stone wall. And the beam is embedded into it, maybe cemented in or something like that, but it sticks out. It's kind of overhanging like a diving board or something. And it's got some, I'm just gonna give it some dimensions here. Let's suppose there's a length L sticking out of the wall. And let's suppose this, for sake of simplicity, let's say this is a square cross-sectional beam. I know we're looking at it from the side, but if we were looking at it from the end, it would look like a square with a diameter D and a height of D and a width of D, okay? And remember, if a longitudinal force is one where you're trying to pull the beam apart in a longitudinal direction, a transverse force would be one where you're trying to apply a force to the end like this, maybe hanging a string with a rock, a weight on the end. That would be a transverse force that you're trying to break it. And you probably see right away that if you were to apply a force downward like this, it would be easier to snap the beam than if you were to apply the same force in a longitudinal direction, kind of trying to pull it out like this to try to break it. Okay, provided it's fixed in there and it's not going to slide all the way out of the wall. So why do we have this intuitive sense that it's going to be easier, and does that is that consistent with a more scientific description of what's going on? Well, Galileo has a strategy for thinking about this. Okay, so I want to explain his strategy, and this is where the law of the lever is going to come in. All right, so I'm going to highlight this point right here, and what Galileo is going to do is he is going to think of this transverse force as applying a torque to this that is trying to break it. Okay, so the transverse force, Ft, applies a moment. I'm going to move this over to here so I have a little bit more real estate to work with. So it applies a moment. Remember, that's the same thing as a torque. Galileo calls it a moment. The more common term to use today is a torque. Ft applies a moment or torque which attempts to break the beam. And remember, a moment or a torque is a product of a force and a lever arm or a distance. So let's calculate the braking moment. I'm going to call that m sub b is the braking moment. And how do we describe this? Well, it's applied by this force right here we're applying to the end, and the lever arm right here. So of this right here, we can think of this point right here as being a fulcrum about which this beam is trying to rotate. So if you were to pull it hard enough, the beam would crack right along the wall, according to Galileo. I know mine's a little bit off, and it would rotate around that point. It would snap down like this, right? So if you apply too big of a force, I'm going to draw maybe the beam when it breaks. It would kind of look like that would be the breaking of the beam. It would rotate around that point, okay? So if that's the force, what's the lever arm? Well, it'll just be the distance from the fulcrum out to the force, which is just the distance L. So that would be the braking moment that is trying to make the beam rotate in a clockwise direction around the fulcrum, right? That's what's trying to happen here. Well, if there is a force, a moment that's trying to break it, and if it doesn't break, there must be some moment that is keeping it from rotating. So what is the supporting moment? Well, Galileo argues that the internal force inside of the beam, the internal resistance, the longitudinal resistance, exactly what I was talking about here, this longitudinal resistance applies a moment or torque which attempts to support the beam. Okay, so what is happening with this supporting moment? Well, remember here we drew this internal resistance like this that overcomes a force that's trying to pull it apart. Well, as you're applying this braking moment, it's trying to pull these little parts apart right here. So we can kind of think of this resistance right here in the middle of the beam, just like I drew it in the middle of the beam right here, that's trying to keep it from rotating down. Okay? So the supporting moment is going to be, we'll call this the supporting moment. And what would be a mathematical representation of it? Well, it would just be this resistive force that's trying to hold the beam together. And here, what would be the lever arm? This is a little bit of a subtle point, but Galileo says that the distance from here to here, from the fulcrum up to the point at which the resistive force, kind of the middle point right here, is being applied, that would be the supporting lever arm. So if this right here was the lever arm, the distance between the fulcrum and the point of the transverse force, then this right here is the distance between the resistive force and the fulcrum. Okay? And what is that distance? It's just d over 2. If d is the width of the beam, it's half the distance. Now, technically speaking, there are countless little resistive forces all trying to hold it together. Some of these are farther away with a longer lever arm, and some of them are closer to the fulcrum, a shorter lever arm, but you can take the average of those, that's the argument, and substitute those with a single resistive force that's halfway up the beam. That is, that resistive force multiplied by a single lever arm of d over 2 provides this supporting moment. Okay? That's the argument, that's the approach that Galileo makes, okay? And here is the main point then. If the braking moment exceeds the supporting moment, then the beam is no longer in equilibrium. That is, it breaks, right? So what's a little bit tricky about this is we're used to dealing with a lever. Let's see if I can squeeze this in here. Like a fulcrum like this, and you have one force like this, force 1, and another force like this, force 2. Force 1 is trying to make it rotate in the clockwise direction. Force 2 is trying to make it in the counterclockwise direction rotate. And if those two moments or torques are equal, then it sits still. Here it's a little bit trickier because now we have a fulcrum right here, but it's kind of like a bent lever. Like here's one lever arm with the force being applied, and here's another lever arm with the force being applied. But nonetheless, this resistive force is trying to rotate it or keep it from rotating in the clockwise direction, and this one is trying to rotate it in the clockwise direction. So those are the competing moments, and as long as those moments are balancing each other, then it's in equilibrium. And if they can no longer balance each other, if the braking moment becomes too big, then it's going to rotate, it's no longer in equilibrium. That is how Galileo is thinking about beam braking using the law of the lever. So let's stop there.